So we're now recording part of the Monday, November 2nd meeting of Math 111 in the morning. We're going to be going over quiz 3 and also the DA from 5.1. So I'm going to share my screen again. And please, everybody, feel free to jump in with questions as you have them. So this quiz has 12 problem parts, all told. Each of them count the same, 10 raw points. And when you get your quiz back, which might be a while, if you're in person, it would be this Friday, you'll see like how many raw points you missed, and also your actual score. Your score would be the proportion of raw points you got, scaled up to be 100. So let's take a look at the solutions here. First of all, there were several scenarios where I described the scenario and then I set up a random variable x, and you're supposed to say if x is a binomial random variable. And if it's not binomial, you got to explain why it's not, okay? But if it is binomial, all you got to do is say how many trials and what the chance of success is. So first one, you roll a fair six-sided die until the sixth spot shows face up, and let x be the number of rolls, including the last one, the one with the sixth spot. So this one is not binomial because it's not based on a fixed number of trials. The first element for being in the binomial scenario is that you've got to have a fixed number of trials. But here, where you think of like a trial as a roll of the die, there's not a fixed number of rolls, because you could get your sixth spot on the first roll or the second or the third or the fourth, so you don't have a definite number of trials. Now, some people said it's not binomial because there's not just two outcomes for a trial. There's six sides to the die, so there's six possible things that could come up. That's not actually the case, because if you're waiting for a sixth spot to show up, then on each trial you either have success, you get a sixth spot, or failure, you don't. So you can take some kind of event that has lots of ways to turn up, and you can construe it as having two outcomes by picking on one of them as the success and everything else is the failure. That shows up later on in the test where there is a binomial random variable, where we think in that very same way. So to get full credit, you got to say it's not binomial, but you also got to give the right reason. Next one, you take a multiple choice test that has 20 questions, and you're guessing on every question, total guess. And on the first 10 questions, you've got 4 choices with only one choice being right. And in the last 10 questions, you got 2 choices, only one of them's right. And you're counting up the number of questions out of 20 that you got right. So this one's also not binomial. This time there is a fixed number of trials. There's 20 trials because every question is like a trial. Every trial does have 2 outcomes. You either get the question right or not. But then when you come to the third element of the binomial scenario, chance of success has to be the same on every trial. That's where this one falls apart, because in the first 10 trials, there's only a 1 in 4 chance for success. And on the second 10 trials, there's a 1 in 2 chance of success. So we can't be dealing with a binomial random variable here. It flunks the third element of the binomial scenario. Part C, standing at a free throw line, taking 30 shots, 60% chance of making each shot. All the shots are independent. Let X be the number of shots you miss. A lot of people correctly said that this is binomial because every shot's a trial. There's 2 outcomes, hit or miss. We got this fixed number of trials here, 30 trials, and people said that, and that was great. But they got, and you know, they're okay with the final element of binomial scenario, you know, because the shots are all independent, so the trials are all independent. This is totally the binomial scenario. This is totally a binomial random variable. There's totally n equals 30 trials. But the chance of success this time is determined by the fact that you're counting how many shots you miss. And so that means you have to think of missing as a success and hitting as a failure. And your chance of success on each trial has got to be 1 minus 60% or 40% here, okay? So this is the kind of question that I noticed that like people who were actually in class when we were talking about this part of the material, they tended to get the question more often than people who were not. And that's because I think I actually like asked kind of like along the way a question like that, where I reversed what was considered to be a success and then said, okay, you know, how would you describe the binomial? So there is, you know, some advantage to showing up for class. Next one, what you expect versus what you get. So you've got some random variable, and we're not telling you much about it except that it's got an expected value of 50.5 and a standard deviation of 5.025, and that its distribution looks roughly bell-shaped. And you don't have to, according to the directions, you don't have to explain your answers here. You just got to say if it's true or false. But I'm giving some explanations down here, of course, in the solutions. So the first part, does the most likely value of x have to be 50.5, the expected value? False, because we've seen examples where the expected value isn't even a possible value for the random variable, you know? So like, how can we conclude that for this random variable, 50.5 is the most likely one? We simply cannot. So an example of a time when the expected value wasn't even possible was the flipping of the fair coin 3 times. If you go back into the chapter 3 slides on expected value, we compute the expected value for the number of heads. It was 1.5, but you can't get 1.5 heads in 3 flips. So lots of people miss that one. Watch out carefully for that one. When it comes to designing the last quiz, I often look at questions that people tended to have a lot of trouble on and then find a way to ask about them again. Is there about a 68% chance that X will turn out between those two numbers? Yes, because the first number is the expected value minus a standard deviation, and the second one is the expected value plus a standard deviation. And the 68-95 rule says that when the distribution is roughly bell-shaped, there should be about a 68% chance of coming within a standard deviation of the expected value. Would it be unusual for X to be less than 53? That would be false. One way to see this is think about that distribution roughly bell-shaped. Okay, picture a bell-shaped distribution in your head. And right in the middle on the x-axis, stick 50.5. The distribution is symmetric around 50.5. Half the area under the curve comes before 50.5. And we're looking for the chance of being less than 53. And so more than half of the area is going to come before 53. So there's like more than a 50% chance of getting less than 53. So it's certainly not unusual for X to be less than 53. So that's one way to see this. Another way to look at it is that 53 is less than 1 standard deviation away from 50.5. And remember, if you're within 2 standard deviations of your expected value, you're not an unusual value. And so it's not unusual to get 53, so surely it's not unusual to get less than 53, because there's a lot more possibility in there for less than 53. Would it be unusual to get more than 68? Well, if you try the z-score on 68, you get that that's about 3, the more than 3 standard deviations above the expected value. So it's very unusual to get something like 68. Certainly be very unusual to get more than 68. Part E, if you repeated the underlying random process 1,000,000 times, like if you tried the random variable x 1,000,000 times and recorded the value of x each time, would the average of the million values be about 50.5? Yeah, because that's actually how we define expected value in this class. It's our informal definition. It's what you get on average when you try the random variable a lot. And we've seen in simulations how when you try a random variable a lot, you get real close to the expected value. So I would say true. Now this number 3 one, this is where there's a binomial random variable using a die. You roll a fair die 600 times, count the number of 2 spots you get. And so there's 600 trials. Each roll is a trial. Success is getting a 2 spot. Failure is getting any one of the other 5 sides. And we're asking here for expected value and standard deviation to fill in those blanks. So you just have to, know the expected value formula for binomials. That was in the directions for the quiz that you needed to know that. It's n times p. So please do 60 times 1/6. A lot of people, like, instead of 1/6, they would do a 0.16, and that's too much round off. I still gave full credit, but it's too much round off. 60 times 1/6 is 100. And for the standard deviation, you've got to apply the square root of n times p times 1 minus p. So using our Leica calculator, you get about 9.128. And so that's how you'd fill in the second blank. Sometimes people would leave off parentheses around the 1 minus 1/6, or they would forget to take the square root, but they would still get some partial credit off of that. People did very well with the boxer dogs. So you got this normally distributed population of dogs, weights, and what's the chance that a randomly selected boxer weighs less than 60? And so people were using p-norm GC just fine. And indeed, the answer is about 0.665. And how much must the boxer weigh so that 75% of them weigh less than her? You're just asking for the 75th percentile. And turns out that you got to weigh 61.72 pounds. So the danger point for a lot of people, the thing you want to really think about for the last quiz, is what's binomial and what's not and why. And secondly, understanding what expected value really is. It's not the thing that you're most likely to get. For some random variables, it is true that the expected value is also the value you're most likely to get. But for a lot of random variables, that is just totally not true. Okay. Any questions about the quiz number 3? Okay, so if you're not quarantined Friday, I can get it back to you then. If you were quarantined, you've already got a copy back. Let's, why don't we close this out and look at solutions for the DA, 5.1 DA. So those have been graded and returned to you. So basically, the way I lightly graded this was if you missed 2 or fewer questions, you got a 10. If you missed 3 or maybe 4, you got a 7. If you missed more than that, you were down to maybe, it was either a 5 or a 6 or something like that. So scenario is that you got a random sample of 765 adults in the US, and 322 of them say that they could not cover a $400 unexpected expense without borrowing money or going into debt. and what's the population that you're actually looking at here. Well, the population is not the sample, okay? The population, the reason we take a sample is because we can't like look at everybody in the population. You know, we wish we could, then we could know exactly what we want to know. But the sample is like just a really small thing compared to the population. The population is all adults in the US, okay? Unfortunately, a lot of people said the population was the 765 adults, but that's our sample, okay? That's not the population. Again, I noticed that people who were in class when we were going over the material were more likely to get the right answer here than people who were not. And I think that's because people who were not, they might have often just looked at the slides, kind of like when you're absent and you get the notes from a friend, but the slides don't say everything. The screencast says more and really tries to address, keep you from confusing sample and population. And I also did that in class. So please do try to be in class and also don't shortcut it. Use the screencasts because the notes, the slides really are not meant to stand entirely on their own. We're not rewriting the textbook when we do slides. We're just giving, you know, I'm just giving myself something that I can then talk about. So the screencast is much closer to what you need to be, you know, processing. Secondly, what parameter is being estimated in this scenario? Is it a population mean or a population proportion? People were pretty much right on that. It's a population proportion. And it's because we were asking them, can you cover the expense, yes or no? You know, so it's a two outcome type of question. What's the point estimate for the parameter? Well, once you know it's a population proportion, then you know your point estimate would be the sample proportion. So all we got to do is compute the sample proportion. So that we can do without any fancy computer work. We can just use our like a calculator. We don't need to go to a data set. I noticed a lot of people like trying to go to a data set. Well, not a lot, but some people would try to go to a data set to get this. But the data's not in a data set. The data's up here in the scenario. Here's the sample size, that's 765. Here's the number who said I could not. And so the sample proportion is the number who said I could not divided by the 765. There you go. What's the name of the quantity that we can use to measure the likely amount by which the point estimate might differ from the parameter? Well, that's the standard error of your sample proportion. And can you compute it? Sure, it's the square root of the p hat times 1 minus the p hat divided by the sample size. For convenience here, I'm setting up the p hat as its own little separate variable that's now going to be in my global environment. And then I can do square root of p hat times 1 minus p hat over the 765. And I'm just calling that standard SE for short. And then this third line here, I'm just printing it out so that everyone can see it. It's totally okay to just compute it all in one line without like any intermediate steps like this. That's totally fine. But anyway, you get about 0.018 or 1.8%. It didn't require it in this question, but I really think that every time you do a sample proportion and a standard error, you should think that sentence to yourself that I've got selected there. Because you're using the sample proportion to estimate the proportion in the population that could not afford. And so you say, we estimate the population percentage is around 42%, but that estimate could easily be off by 1.8% or so. You know, you can be off by a standard error or two. Now, suppose that some cable news pundit thinks that the population proportion is actually 50%. Should she be surprised to learn that when we took a sample, we got 42%? for that, you can use the z-score as a measure of surprise. And so you compute the sample proportion minus the p that the news pundit thinks that the population proportion is over the standard error. And so the p hat minus the 0.5 over the standard error. And that turned out to be minus 4.4. And so that's just like really unusual. I mean, like if the pundit were right, if p were really 0.5, this p hat would be like more than 4 standard errors beneath what it would be expected to be. So that would be like crazy. So the pundit should be very surprised by this data. She should be willing to revise her view about what p is based on this revelation from the data. And so we're going to see this theme a lot in future chapters, comparing, using something like a z-score to compare what we get in the data with an opinion that someone might have before they see data. And that can help the person who has that opinion decide whether they need to revise their opinion based on the data. Okay, so that is the DA. Elements of that DA are definitely showing up on the quiz. Check those directions for quiz 4 again, and you'll see these topics coming up again. Any questions on the DA? Let me stop for a moment and check on that. We got almost everybody here. That's great. Got 19 folks. Okay. Let's go to RStudio then and see what we have got for today in section 5.2. So I'm going to take away this DA. And maybe if you have anything in your global environment, go ahead and press the little broom to get it clear. Sometimes I even like to clear my console. I push, there's like a little broom I can push there. And over in slides, you'll be wanting to study 5.2 confidence intervals along with the screencast if you have not done so already. I've opened up those slides, so I can leave there. The DA that's due on Tuesday, hey, let's get that. So DA, OS 5.2 confidence intervals, file save as, ... twiddles, find my submit by double clicking and say that I want to save there. Okay. Oh, one more thing. I think I want to stop recording the meeting now that I've done this, the going over of things. So I'm going to stop the recording.